Right. In Lab 1, you're going to be looking at simple harmonic motion. And simple harmonic oscillators are objects that have a repetitive motion. An example could be a pendulum swinging back and forth, or a mass on a spring vibrating back and forth, or even something undergoing circular motion. So the first thing you're going to do is you're going to look at those three types of objects. So you can compare their motion. It's obvious that they are moving and that they are making the same number of repetitions to their motion every second. You can see that the pendulum and the mass move back and forth at the same rate, as well as looking at the object on the circular table. So you're going to be making some basic general observations about that. Then you're going to actually measure the period of oscillation for these three objects. They are making one complete oscillation, whether it is a pendulum that starts at the left, moves all the way to the right and back to the left, or the mass that starts at the left and moves all the way back to the left, or an object undergoing circular motion that starts on the left-hand side of the circle and ends back up at the left-hand side. So to do that, you're just going to fast forward until you see the black object on the table, and you're going to stop it. So you want to make sure that the hand is not touching it and that it is as far to the left as it can be. And you're going to click on the stopwatch, and you're going to click on the circle arrow there, and that will zero it. And then you can play it and stop it when it gets and has made one complete rotation. So that's with the black object on the circular disc. I'm just looking at where I'm stopping at where it returns back to the point that it was released at. So it looks like it's about 2.23 seconds. And you guys all will get something a little bit different than that. But that is the time for one complete oscillation. And you want to make sure that when you type that in, that you just type in the numbers that it's giving you, 2.2333 seconds. Make sure you put the units on it. And then you're going to calculate the frequency. And frequency is just the inverse of period. It's not how many seconds per oscillation. It's how many oscillations per second, or hertz. So you will take that 2.2333, and you will take the inverse of that, 1 over 2.2333. And that will give you the hertz. So make sure that you keep the same number of decimal places that you had for the period, the same number of decimal places for the frequency, and the units will be hertz, HZ, or seconds to the -1. And then you're going to find the angular frequency, because remember that even though we have a pendulum that's moving left to right and a spring that's moving left to right, this circular object, if you were to look at the top-down view of it, it would be actually traveling out radians per second. And so when we draw a position graph, it's going to end up being some kind of sinusoidal graph. And when we take the sine of something, it's got to be an angular term. So you need to be able to convert the linear frequency, right, the non-angular frequency hertz, into, instead of 1 over seconds, or seconds to the -1, it needs to be radians per second. So remember that in one complete oscillation, you have 2 pi radians. So you're literally going to take 2 times pi on your calculator and multiply it by the frequency that you found in 3. Okay, the next thing you're going to do is you're going to look at an additional video, this video, and you're actually going to set up a ruler, and you're going to, at different times, you're going to measure its position. And so what we want to have is when we click on the ruler, we want the 0 position, which is our equilibrium position. And we're going to actually look at the mass that's oscillating back and forth. So what I'm going to do is I'm going to go back until this is at 0 seconds. Or where I think it should be at 0 seconds. Right there. I'm going to back it up just a teeny bit. Okay, and now I'm going to look at where the mass is. And now, first thing I'm going to do is I'm going to go ahead and zero this out again at that point. And now I'm going to be tracking this red mass moving to the left and right. I'm going to track its position. Every so often, I'm going to record its position. And I think what we'll do is maybe every 0.5 seconds. But first we had to find that start point, and we had to zero it. So I did that. Next thing we do is we turn on the ruler, and if we click on the ruler, we can move it so that we have an equilibrium point. And the equilibrium point is where the 0 is going to match up to the middle of that circular, of that nut on the circular disc. So I'm going to arrange my ruler so that the 0 is the equilibrium point. It's the center point of the oscillation. If I want to know the amplitude of the oscillation of this mass, notice that the mass was pulled, if I look at it, to a position of negative 22 centimeters. And then it's going to be released, and every 5 seconds we're going to track its motion. But my first point on this graph is going to be at 0, it's going to be negative 22 centimeters. And then I'm going to now increase it until it gets to 0.5 seconds. Right there. And it is at, and actually, you know what? I think I'm going to go every 0.250 seconds. And that way we'll get enough points here. So let me do that. Let's go back to 0.25. And at 0.25 seconds, it had a position of negative 13 centimeters. So I'm just going to type in 0.250 and negative 13. We don't want to drop that negative because it's oscillating back and forth from the left side to the right side of the 0 point. So we want to make sure we do record that. Now I'm going to advance it up to 0.5 seconds. And it now has a position of 4 centimeters. And once again, I'm just reading that, the middle line on the yellow piece of paper. So this is at 0.50, negative 4. Now I'm going to keep taking points every 0.250 seconds until I've made 2 complete oscillations. So I started at negative 23, and then I'm going to go over here to the positive side somewhere, some maximum distance there, and then I'm going to go back to around negative 23, and then I'm going to go back out to some positive term, and then the second time that I return back to negative 23 will be 2 complete oscillations. So I start at the left point, go to the right, return to the left, that's 1 oscillation. And then I repeat that 1 more time. So I'm going to take data every 0.25 seconds. As I collect data, I'm going to need to add rows. So I'm just going to click on the 3 dots and insert a row below. I'm going to go ahead and do that for a few more of these points. I'm probably going to need about 10 rows, but we'll see. So you end up getting about 19 points, 19 to 20 points. And now we're going to make before we make a graph, let's make a conversion and change our centimeters into meters. So to do that, we're going to add a new column. So click on the three dots beside position and insert it to the right. And the name is going to be position in meters. So you can either do this manually and just divide each of these by 100 or, oh, and by the way, the variable is an X like it always is. Okay, so I'm going to add a formula though, just to do it for me. So I'm going to go change column formula, and I'm going to take the position and I'm going to divide it by 100 and press submit. So there's my new position in meters. Now I'm going to graph position on the y-axis. So, and I want the position in meters. And then I want, on the horizontal axis, I want time. So this is a position versus time graph. Notice that it looks like it is some kind of sinusoidal graph. Now we can't really do a curve fit here, okay? But we can see that this thing is going up and down. And it looks like, you know, the maximum, if I measure from the 0 point here and I measure the lowest point, it looks like it's negative 25 meters. And the highest point is 0.25 meters. So it's oscillating between negative 0.25 and positive 0.25 meters. So that means the amplitude of this sine graph is 0.25 meters, the absolute value. So we're going to talk about the type of motion here. So a position graph, and let's go ahead and put the title in, position versus time. A position time graph that's linear indicates constant speed. Well, this is not linear. If it were a quadratic parabola, it would mean constant acceleration. So it's not traveling at a constant speed, but it's not traveling at a constant acceleration. So you can say that it has a non-constant acceleration. It's accelerating, but not at a constant rate. And that makes sense because think about it. When you take a spring and you stretch it, it gets harder to stretch it, right? Because the force that you're counteracting, the restoring force of that spring, is actually proportional to the displacement that you stretch it or that you compress it. So the more you compress it or the more you stretch it, you have to exert more force because of this elasticity. And if the force is not constant, then the acceleration is not constant. So it's accelerating, but at a non-constant rate because there's a non-constant force acting on it, the spring force. So you're going to describe that motion, and then you're going to write a function. So we've already said that the generic formula for the position function is going to be the amplitude times sine of whatever the angular frequency was. So for example, if the amplitude is 0.25 meters, and you calculated the angular frequency to be, I don't know, I'm just making up numbers here, 4.230 radians per second, then the formula would be x equals whatever a is, 0.25 meters times sine of 4.230 radians per second times time in parentheses. So you just want to make sure that when you write that equation that you actually write it out using the units and that generic formula that we talked about. Now, it turns out that the velocity of this is going to be whatever the amplitude is, the maximum velocity, which occurs when you think about it. When you watch this thing, these objects going back and forth, it comes to a stop at the endpoints, right? That mass comes to a stop, and it actually turns around. So the endpoints, the maximum displacements, are where you have the most acceleration going on because it's actually changing direction and speed. But in the very middle of its motion at equilibrium, that's where it is traveling at the fastest speed. So it comes to a stop on the endpoints and turns around. It has more acceleration, maximum acceleration at the endpoints, and more velocity, maximum velocity at equilibrium, at the 0 point, the middle point of its motion. And that maximum velocity is just going to be the amplitude times the angular frequency. That'll give you meters per second. And if you take the amplitude times the angular frequency squared, that will give you the acceleration in meters per second squared. And that's pretty much the lab.